Now, fraud is bad, but almost certainly, most of the replication crisis, the fact that the scientific results can't be replicated and are probably false, is not due to conscious fraud, it's due to self-deception, where the researchers have actually fooled themselves as well as the referees in their papers. Three main types of this unconscious fraud, this unconscious bias, p-hacking and publication bias, and we'll talk about these in turn. Let's start off with unconscious bias. Now there's a famous example of this in physics, which is the Millikan oil drop experiment. This is an experiment that measured the charge of an electron, done back in the early part of the 20th century. Originally done by Millikan, and the original result got a value for the charge of an electron which was too low, and the reason why it was too low is that Millikan used the wrong value for the viscosity of air in his experiment. But then after that event, a whole bunch of other experiments were done over the years, and these used the correct value of viscosity, so they should have got something similar to the correct value for the charge of an electron. But in fact, for a while they kept on having values that were too low, and then 20 years later they crept up towards the true value. So how come these studies over here, which were using the correct value of viscosity, still got too low an answer? Why did it gradually creep up towards the correct answer? Why didn't people start getting something similar to the correct answer right away when they used the correct viscosity of air? And the normal idea is when you're doing any sort of experiment, you've got lots of complications. Have you calibrated this correctly? Have you allowed for that? Have you thrown out the wrong data? People always throw out discrepant things or maybe redo discrepant observations. Should you analyze it this way or that way? There are lots and lots of choices, literally hundreds of choices when you're doing a difficult experiment. And let's say you do the experiment and you get an answer it's different from what the famous Nobel Prize winning Millikan got. You might think, maybe I have another look. I'm getting a different answer from what this famous person got. Yeah, maybe I should have calibrated this differently, or maybe I should have thrown out a few more discrepant points or something. Whereas if you get an answer that's coming out similar to what people have got previously, maybe you don't put such effort into checking everything. A similar situation happened in astronomy when you're measuring the Hubble constant, which is the rate of expansion of the universe. This is originally measured by Edwin Hubble, and he got a value that was much too big because he was using what he thought were stars in nearby galaxies and measuring their brightness. But what he thought was a star was actually a cluster of stars, which is why he got it wrong. But as time went on, people got better and better measurements, and the number gradually drifted down to what we believe to be the current value, which is about 70. So similar sort of thing to Millikan, people were getting, if they got different results from what the famous Nobel Prize winning Edwin Hubble got, they would maybe look at it really hard, whereas if they got a similar answer, they'd maybe not study it so much. But then when they got down to the 60s to the 80s, there's a huge scatter, and you can see there's something tiny error bars here and tiny error bars there that do not overlap at all. And so for a long period we had what we got something called the Hubble Wars. This is between Alan Sandage and Gerard de Vaucouleurs, two very famous and eminent astronomers, and they got very different values for the Hubble constant. Sandage got a low value, about 50 kilometers per second per megaparsec, and de Vaucouleurs got a much higher value, about 100. And this wasn't just different error bars, they both had small error bars that didn't overlap any way, shape or form, so they couldn't both be true. And for over decades, each of them remeasured and always got the same answer, a low answer for this group, a high answer for this group. And again, we think there was subconscious bias. This is a really difficult thing to measure, and you have to make lots of choices. And if you believe the value is 1, then maybe subconsciously it's pushing you towards making those choices in how you set up the experiment that form it that way. So sort of choices, what data to include and what to reject, what possible problems to focus on. Do you think something's going wrong in your experiment? Maybe your vacuum pump isn't working fully enough, maybe there's a bit more friction than you thought it would be. There's always a million things that could go wrong, and which of them do you pay attention to? When is the result good enough? You finally got to a result, do you stop, or do you think, yeah, but I'm not sure, maybe I'll just go and do a few more tests? What assumptions and approximations are reasonable? Everyone has to make assumptions and approximations. The world is far too complicated otherwise, but were they sensible ones? And so whenever you're making a choice, you have to make these choices, and it's too easy to get biased. often subconsciously. The worst situation is when things are political. So if you're doing politically charged and difficult research, so many people would say, the right-wing opponents of climate change research would say this is what's happening in climate change research. Coming up with these models for climate change is really hard. A lot of assumptions and approximations have to go into them. And if you know the answer is that climate change is going to be really bad, then can we really be sure that at some subconscious level you're not making these sort of decisions in your analysis that give you that answer? Research about something like gun control, again, very easy to be biased one way or the other. Educational research is a classic example. People have very strong opinions about the best way to educate. Again, these are difficult experiments to do, and it's very easy for your subconscious bias to push your result one way or the other. Or nutrition, also a situation where people have strong passions, experiments are difficult, and so it's very easy to subconsciously push things one way or the other. What's the cure for this? Well, in physics we have a cure. It's called blinding, and this is now widely used in major physics and astrophysics projects like measuring the Higgs boson. Modern surveys looking for the Hubble constant, for example, use this. The idea is you take your raw data, and then you have the A team who will add a constant to it or multiply it by something. So then this number with this unknown constant added is sent to the data analysis, to team B. They will analyze the data, and they will get a value of the Hubble constant, but they'll know that the value of Hubble constant they get is not the correct one because this unknown constant has been added to the data by team A. Once they've done their best bet and say, I think, given this data, we think the Hubble constant is 62, then team A will go and subtract the constant they first added, and then they've got their final result. So that way the people who are actually making all these decisions about how to analyze the data, how to do the experiment, don't actually know what answer they're going to get, because they know that something's been added to the data. So that's what makes this whole sort of unconscious bias impossible, because you know perfectly well the answer you get is not the correct one. There's no point in comparing it to anybody else's consciously or subconsciously. You've just got to do the best you can with the data you've got. So this is now widely standard in big physics and astrophysics projects, and it's one of the reasons why at least the big projects in physics and astro have a good reputation. It's not done so much in small research groups, and maybe that's a problem. It can also be done in like psychology and medical research. For medical research, the gold standard is the double-blind trial. First of all, the person let's say trying to work out if a drug works. Half the people will be given the real drug and half will be given a placebo, and they won't know which one they're getting, because if they know whether they're getting the real drug, that might influence them. But also the researcher who's doing the data analysis should not know, which is what makes it double blind. So you're just given here sample A, sample B, which one has the better result, and you don't know which ones had the drug and which had the placebo. It's only later, once you've done your analysis and come to the conclusion, I think sample A are doing better by 5%, then they reveal whether that was the one that has the sample or not. So it is time consuming and difficult, but it can definitely work, and it's a pretty good solution to this unconscious bias problem.